Probably, and they're all assumptions, which is really nice. It is really short, yeah. Okay, so we talked about acids and bases a little bit yesterday. We discussed about how you have all these equations that you can use to solve for pH, solve for pOH, solve for H+, whatever, hydronium ion concentration, all of those things, okay? So something in addition to just like knowing that there's acids and bases is the relative strength of them, okay? And so the acid strength is defined by the equilibrium position when it is in equilibrium. So a strong acid is one whose equilibrium lies far to the right, which means that it's going to completely dissociate, okay? And so that's why it just makes sense, what we did yesterday, that if you know the hydronium concentration, then you could just use that and solve for pH and plug that in to your equation and go for it. Because it completely dissociates, the products will be more prevalent because of its position. But when you have a weak acid, the weak acid actually has the equilibrium lie to the left, meaning that most of the acid, even when you place it in for the reaction, is going to stay present together. It's not going to dissociate as much. So it only dissociates a little bit, which means that a majority of it won't. So the concentration of the hydronium ion is going to be significantly lower because it doesn't dissociate, okay? And so when it is a weak acid, then we have to do a little bit extra to figure out pH and all that kind of stuff. So there's two things that we have to consider when we're figuring out our pHs. Then, again, remember hydronium ion, H+ ion, they're really interchangeable. I'm trying to force myself to use the hydronium myself, but I've got some old stuff that doesn't have it there yet. So we have to think about the acid that's involved, and also how does it react with the dissociation of water. Okay, so for a strong acid, since it has a far left position, then it's going to just completely dissociate. So when we're solving for pH of a strong acid, like I said, whatever the hydronium concentration value is, you just plug that in. Yes? Is that a typo? That is a typo. Wait. I know what I'm trying to talk about here. Okay, so it's talking about, when it says far to the left, it's talking about the water equilibrium. So it's talking about this equation right here, not the acid equilibrium question. So that, when it says far to the left here, it just means that the water is not going to break apart. The water is going to stay liquid. So the H+ from water breaking apart will have no factor in the pH for the acid. Okay, yeah, that's a good clarification. So basically, if it's strong acid, the water does not affect the pH. Only the acid does. Yes.
And then for weak acids, is the water equilibrium part of the body?
Yeah, no. It'd still be, well, I think it will still be for the left for that one too. We'll go through. It's going to be more in 8.3 about that. Yeah. Okay, so basically we did this before, this example, so we're not going to do both parts. Let's just do one part. What that whole thing was saying was, if you know what the concentration of your acid is, then that also tells you the concentration of the hydronium ion or the H+ ion. So it's really easy to solve for pH, okay? We did this in a lab when we did our titration this year, where let's just do A, okay? So if we have a 0.1 molar solution of nitric acid for A, then we want to know the pH of that. And if you look after the example, I have a list of strong and weak acids. So nitric acid is a strong acid. So we assume that it will completely dissociate. So the dissociation of that, or the net ionic equation for that, it wouldn't be an equilibrium arrow. It would just be a regular arrow, okay, because there won't be any change back. And that means that we'll have the complete concentration from the acid will also be the complete concentration for the hydrogen ion, and it will be the same number for the nitrate ion. So when we're trying to find pH, we can just assume that the concentration of the H plus or the hydronium is going to be that 0.1 molar. Okay, and so since that is the 0.1 molar, then we can just take the negative log of the 0.10 to get the pH value, which is 1. The negative log of 0.1 is 1. And so just a reminder from yesterday, the number of decimal places within the log tells you the number of, the number of significant figures within the log tells you the decimal places on P. Okay, so since it's 2 significant figures, we should technically report it as 1.00 for that. Okay. No, pH does not have a label. You don't have to label that anything. POH doesn't either. So this is technically just the math for A, but if you were to do the B example yourself, too, same thing applies. Hydrochloric acid is a strong acid, so we know it will completely dissociate. So the 1.0 times 10 to the negative 10 molar would be the concentration of the H plus. So then you just use that number to find pH, which it is 10 if you wanted to solve. Okay, so common acids that you need to know, okay? So there are 7 strong acids that completely dissociate. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perfluoric. So those 7, they're good to just recognize that they are. And then these are just some examples of weak acids. There's a whole lot more. But like phosphoric acid, nitrous acid, which contains the nitrite ion, hypochlorous, acetic acid. I put that in 2 different ways because there's multiple ways to show that. In chemistry 1, we learned it, the AHC2H3O2, that acetate ion. We wrote it like that. But you might see it in textbooks and stuff. You might see it in textbooks written a different way, like this, or even they might switch around the C's, whatever. It's all that stuff. So it's just good to have an idea of what that is. And then when we get to 8.3, you're gonna know because you're gonna be given a number when it's a weak acid, so you'll be able to see that even better. Okay. It's also important to note that sulfuric acid is the only acid that has 2 H's on the strong acid list. So that means that we call it diprotic because it has 2 acidic protons. Remember, protons are the H plus. So sulfuric actually can lose 2 H's when it breaks down, when it dissociates. But we'll talk more about that strength later, which one's actually more important, and all that kind of stuff. Okay, so that's a nice brief overview. Also, some of the most important acids don't actually have an acidic proton attached to an oxygen atom. We call these hydrohalic acids, like the hydrochloric and the hydrobromic and the hydroiodic. They have a halogen atom as the anion, and so those are a majority of the strong acids. Hydrogen fluoride or hydrofluoric acid, that is technically not considered a strong acid, but is anybody a Breaking Bad fan? Ever watch that show? You know when he dissolves the body in the bathtub, he uses hydrofluoric acid. So it is very reactive, but we just don't, we don't consider it to completely dissociate, so that's why. Okay, so now let's talk a little bit about bases. So, no more dissolving bodies. Okay, so Arrhenius' concept said that bases contain hydroxides. And that works for something. But according to the Bronsted-Lowry model, in general, a base will accept the proton. Okay? So in both models, things like sodium hydroxide and potassium hydroxide fit the descriptions for both of these because they, one, contain hydroxide ions, they fit the Arrhenius concept, but then they also will completely dissociate, so they'll be able to grab those hydrogen ions around. So we call them strong bases since they do fit both criteria. So some more things about strong bases. Technically, any cations that are from group 1A, which are the alkaline metals, or group 2A, the alkaline earth metals, on the periodic table are strong bases. So basically, if you see a hydroxide and you know that it's a base, but you're unsure if it's going to be strong or not, if it has hydroxide, it's strong, okay? And it will usually just be columns 1 and columns 2 for that. But it's important to know that the 2A, since it has a +2 charge, will actually contribute 2 moles of hydroxide. So the concentration of the hydroxide ion is twice as big because it has 2 for every 1. And also, most alkaline earth hydroxides are not very soluble, but they have advantages. So, like this one's called milk of magnesia. It's magnesium hydroxide. It's used the same as Alka-Seltzer, which is the same as Tums. It just like settles your stomach from indigestion or heartburn. And Tums has calcium hydroxide in it, and I think these have bicarbonates in them, but they're also different types of things. So we can use some strong bases for, calming acid reflux and all that kind of stuff in our bodies. So they do have advantages there. Okay, so because strong bases completely dissociate, the hydroxide ion concentration at a strong base is equal, I think that's a typo, sorry, is equal to the initial concentration of the strong base. So this, if it's like this in your thing, sorry, this should be equal. I typed that wrong. Which from there, then it would just be the same to solve it like we did. The only difference is you have to be careful that you're thinking about when you're plugging in the number, you're plugging in hydroxide, or you might solve for POH. So you just have to be careful with this. We'll practice those more on Friday with those practice problems. Okay. And that is it for, let me stop recording.